Greetings, everyone. I would like to welcome all to our 2021 TEIN Winter Workshop, which is dedicated for the personalized dosimetry for radiodiagnostics. So I hope you enjoy the lectures, and I will deliver some brief introduction about this dosimetry and radiodiagnostics. So I want to inform you that if you have any questions or comments in between these lectures, you can just freely write down at the chat. So then we can actually discuss it right after the lectures or at the session, like questions and Q&A and discussion session, we can discuss more. Okay, so although it's late, Happy New Year again, and I will start some introduction. So as I think I already have shown you about this slide, that there has been increasing interest in the diagnostics and especially therapy. So like keywords like therapy or PSMA or dotatate has been emerged in the Journal of Nuclear Medicine abstracts. So diagnostics, as I have, diagnostics is a combined word of therapy and diagnostics. And the beauty of this diagnostics is that you can actually see who will have the response. So you can choose, using this imaging isotopes, you can actually see who will get response. And after choosing this patient, you can actually deliver this therapeutics using the, just changing the radioisotope to the therapeutic agent, such as lutetium or yttrium. So this concept has not been new, but it has been used for decades in our nuclear medicine fields, like radioiodine therapy. So like as in this case, you can see actually after the therapy using this iodine scan, whether this patient will have a response or not, we can actually predict. So as assume that after the second therapy, this patient had a response of like almost a complete response to this radioiodine therapy. So samely, this concept was adapted to the right now neuroendocrine tumor patient therapy. So firstly, using this gallium dotatate imaging, you can actually see who will get the response. And you can choose the patient who will have a better response to the therapy. And then you can apply this lutetium therapy, and then this patient will have better effect. So, and what has been emerging is that using these imagings and after these post-scan images, what we can actually do is actually we can calculate how much dose will be delivered or how much dose will be delivered to other normal organs. Or after the therapy, what we can do using this post-therapy scan is we can actually in real calculate the dose of how much was delivered to the patient or the tumor and the normal organ. So that's the concept of dosimetry. So dosimetry is a calculation and assessment of this ionizing radiation dose. But actually, for nuclear medicine, this is not adapted to a daily process. However, for the radiation oncologist, this dosimetry is actually a daily process of what they do. So every day they draw this kind of ROIs in the tumor and normal organs. The purpose is to deliver the most radiation to the tumor and at the same time preserving the adjacent normal tissues. So we call in some way like painting those, or we can call it like the art of radiation. But also in the nuclear medicine, we are actually familiar to this kind of dosimetry calculation. which is actually applied for therapy of hyperthyroidism. So when we apply iodine therapy to this hyperthyroidism, actually there are many methods to calculate the doses, but one way we can actually calculate how much will be delivered to the thyroid tissue based on the thyroid volume and maximal iodine uptake and the iodine half time. So in the diagnostics then, why should we do this dosimetry? Is the purpose I already mentioned is that to deliver a lesser radiation dose to the lesion, which is a target lesion, mostly it may be the tumor, and at the same time without causing undesired effects in other normal tissues. So then how can we achieve this purpose? There are like two main strategies. So it can come from this concept of AHA-assay, which is as high as safely administrable. So for the first part, as high is actually the first strategy will be delivering as high dose to the tumor. So in this strategy, the importance is in the dosimetry of the tumor itself. So we have to calculate how much dose will be delivered or is delivered to the tumor is important in this strategy. But however, this strategy has some limitations because in case of patients with like metastatic lesions, or if there is too many disseminated metastasis, we cannot actually accurately calculate the dose. So the second strategy is more focusing on this non-target organ at risk. So the purpose is to deliver the maximum tolerable absorbed dose to this non-target lesion, which can be reflected as safely administrable. But for the different radiopharmaceuticals, actually the organ at risk are different. As you will know, this iodine 131, the organ at risk that we should have care is actually the bone marrow. And for the radiation embolization therapy, the organ at risk might be liver or lung. And for newly advanced this lutetium dotatate or lutetium PSMA therapies, the organ at risk might be kidneys or bone marrow. So these are actually decided by the biodistribution of these agents. So the strategy is to give the maximum tolerable dose, which is the threshold dose for the normal tissue to have toxicity, to have no toxicity. And at the same time, when you give this maximum tolerable dose, actually you can achieve the higher dose to the tumor itself. So in many studies, this maximum tolerable absorbed dose method has been actually applied for the personalized dosimetry. And how should we decide the threshold dose is the problem. So for the normal organ, the threshold, there has been many studies. So for instance, for about the thyroid cancer, there has been a studies regarding this dose and effect relationship. And they have seen that when the threshold dose for the bone marrow, like blood and bone marrow, is actually too great. So if it exceeds this too great, they have shown that there are many patients who suffers from toxicity, like more than grade 3 of bone marrow related toxicity. So now, and in other radioisotopes, also there has been studies to see dose effect relationship to figure out how to select this threshold dose for the maximum tolerable absorbed dose. But still, it is actually in real, calculating this dosimetry in the clinical situation is is quite difficult and more time consuming. And in some case, it may require experts like medical and nuclear physics. But then there should be a reason why we should do this personalized dosimetry, although it is too difficult or time consuming. So there has been some researches regarding the efficacy of applying this personalized dosimetry. Now we can start from the thyroid cancer. So there has been a study of applying this maximal safe dose strategy for the iodine therapy. And you can see the important point of this study was the enroll criteria was the patient who had no evidence of response. So the patient who doesn't have response to iodine 131 at the fixed dose was enrolled in this study. And to these patients, the iodine 131 was given at the maximum safe dose. And the maximum safe dose was the dose which reached the blood or bone marrow dose to 2 gray. So the mean calculated dose was 12.5 gigabecquerel, which is actually was more than the fixed dose, which we have empirically delivered to the patient. And interestingly, surprisingly, you can actually see, although these patients all had no response to this fixed dose, they had more than 45% of patients had response. And like when you consider the disease control rate, it was almost 90% of patients. But you will also be curious about whether if you administer such a high dose, maximal safe dose, whether there will be more toxicity. And actually there has been, they reported there has been a cytopenia, but these were actually transient cytopenia, which recovered after a few months. And more interesting study was reported in 2011 about comparison between this personalized dosimetry versus the empirical fixed dose method. So as you can see, the strategy was same to give the dose which reaches the blood and bone marrow dose to 2 gray. And as you can see, there was actually a benefit from the survival. And also when you see the toxicity regarding bone marrow related toxicity or xerostomia, you can see there has been no significant difference between this dosimetry-based personalized dosimetry or fixed method. And as you can see from this mean calculated dose to dose, you can see that the patient had more dose delivered, which actually consequently have shown a more favorable result in the survival. So, and there are also some evidence from the radioembolization therapy. So right now, the commercially available agents are Therasphere and Thersphere. And there is a insert, a label, how to calculate the dose. However, in the clinical situation, those calculations are the different institutions are using different methods to calculate the dose, how much dose we should administer. So before that, normally we take this technician MAA scan before the therapy. And the purpose of doing this MAA scan is to actually calculate the hepatopulmonary shunt function. So as I told you before, that the risk in organ for this radiation embolization therapy will be the lung or the liver. So if there is no hepatopulmonary shunt, the lung will be preserved. So actually for like these radioembolization therapy, there has been a contraindication if like pulmonary shunt is more than 20%, it should not be administered. So, and like less than, if it is like between 10 to 20, then you can actually, the physicians can adjust the dose to administer. And the next purpose will be to identify patterns of extrahepatic activity which may pose a contraindication to this therapy. However, there has also has been applied, some institutes have applied other methods for choosing the dose of administration. Actually, the main purpose of this study was to show a prognostic score to predict response to yttrium therapy. However, what we should actually focus on is how they have chosen the dose. So they used this maximal safe dose method, and they chose the liver as the organ at risk. So for the initial 18 patients, they have chosen the dose which reaches the maximal dose of liver as a 40 gray. And they have seen no toxicity in these groups. And also they have seen that more than 70 gray, the patient can talk when there is they have seen that the threshold can be heightened to 70 gray. So for the next 100, more than 100 patients, the dose was given to reach the maximal dose up to liver as a 70 gray. So using this method, what they have shown was the median overall survival was 14.1 months. And actually, it was relatively had more improved survival compared to the empirical method, just using the tumor volume. So actually, they have shown that when delivering this maximal safe dose, we can have some more gain in the survival. However, the limit is that it is not a head-to-head comparison of the dose method. So it should be, these limitations also should be considered. And going on, there is now a more emerging interest in this PRT therapy, which was actually discussed previously at our summer workshop. And so currently it is being investigated as a treatment for prostate and also neuroendocrine tumors. So you can apply yttrium or lutetium for the therapy. And with this clinical phase 3 trial for the mid-gut neuroendocrine tumor, it has shown very improved progression-free survival or overall survival result. And by these promising results, they have actually got an approval of using this lutetium dotatate to the clinic. However, as you can see, what they have got approved is when you see the label of this Lutathera, you can see that it just uses a fixed dose method of 4 cycles, 200 millicurie for 4 doses. So they haven't shown that whether applying a personalized dosimetry will be applicable or not. So now they are in the clinic, we are only applying this PRT therapy in a fixed dose. However, there is an ongoing study to see whether applying a personalized dosimetry for the PRT will be applicable or not. So actually, in this Illuminate study is also a maximal safe dose. It also applies a maximal safe dose strategy. And the organ at risk in this PRT therapy is focusing on the kidney. So at the first step, they have chosen the dose which reaches the kidney dose to the 27 grade. And if the patient has a response or stable disease and without any toxicity, they can move on to the next step, which has a dose reaching 40 grade to the kidney. And as you can see, the patient had variable cycles of administration of this lutetium dotatate when applying this method. So as you can think, when you just apply the previous in the dosage, the form that Lutathera uses, you can only use this 4-cycle method of 200 millicurie. However, like many patients had got various cycles, more than 4. And right now, and for the toxicity, they have shown some relatively decline in renal function, of moderate renal function decline. However, the grade 3 or 4 toxicity was not observed. So they are now still ongoing, and they will show whether this will be applicable or not. And the next part will be, next study is about PRT, and this also applies a maximal safe dose strategy. And the dose they have chosen was 23 gray to the kidney. And the first dose was actually derived to reach the 5 gray based on the body surface area and GFR. And second to fourth dose cycle was decided based on the previous cycle, previous cycles and the image scan from the previous therapy to reach 6 gray for each cycle, and which sum up to 23 gray to the kidney. So what you can see is at every cycle, they adjust the dose to give to the patient. So you can see here that the first dose given was 9.7. However, the second was 14.6, and the third was 21.9. So the difference is that although the delivered administration dose to the patient differs, what the purpose was to reach the kidney dose is at the same level of 6 gray. And when you apply this kind of method, what they have seen was there was more patient having beneficial effect of response, like more than almost 50% of patients had a response. And compared to the simulated fixed dose, you can see that there is a more injected dose to when you apply this personalized dosimetry. And accordingly, you can imagine that compared to this fixed dose method, there will be more absorbed dose to the tumor itself. But however, at the same time, the toxicity was not significant, although there were some grade 3 or 4 toxicities related to the bone marrow toxicity. And there were quite a lot of, more than 50% of patients showing lymphocytopenia. However, again, these patients were transient. So this study will now further show whether they have shown a efficacy or not in the following studies. So we have seen in various disease conditions that applying this personalized dosimetry will have efficacy for the treatment of the patient. And now we should know how to actually calculate this dosimetry. So actually, it is based on mostly the organ-based dosimetry. So this organ-based dosimetry is a standard method in nuclear medicine field, and it is actually simple and fast to calculate using it. So the importance is the most important concept is to calculate how much target organ absorbs dose from these all different source organs. So the target organ itself can be a source organ, and there can be another source organs adjacent to this target organ. And you should calculate all the cumulated activity, sum of cumulated activity from the source organ. And if you multiply by a normalizing factor, you can actually achieve a dose, absorbed dose to the target organ. So for example, if you want to calculate the absorbed dose in the liver, firstly, what you should decide what are the source organs. So normally, when you see the biodistribution image, source organs are the organs which will have significantly higher uptake compared to the background. So in this case, for the PSMA, you can think that liver itself can be the first source organ, and salivary gland or spleen and kidney or bladder can be a source organ. So these can be source organs. So now what you should do is you should actually calculate the cumulated activity in these each source organs. So what you should have to do is you should acquire a multi-time point data. And then why you should earn this multi-time point data is then you can get this time activity curve for each organs. And after achieving it, you can actually calculate the area under curve, assuming for the infinite time. And this area under curve will be the cumulated activity for each organ. So if you sum all these cumulated activity in each organ, you can now get the sum of this cumulated activity. And then next step is to apply this S factor, which is actually derived from, you can actually get information from the mole tables or other pamphlets. And this S factor, it depends on the radiation type or energy or anatomical relationship. So for example, what you can imagine is this, it is the MERD table for the iodine 131. And as you imagine the source organ as a thyroid, this thyroid will have an effect for instance, if you choose the target organ as lung, the thyroid will have quite effect. However, the most highest effect from the thyroid will have an effect in the thyroid itself. So as you can see, the S factor is the highest in the thyroid. And if it gets have more distance from this source organ, the S factor will decrease. So this is kind of factor that can actually normalize the relationship between this anatomy relationship, and also it differs from what kind of radioisotope you will use, the energy of the radioisotope. So this S factor is actually energy transfer from source organ to target organ, and it is computed by the Monte Carlo simulation from this average man. And the assumption at this average man calculating this S factor is that organ has a uniform activity and medium distribution. However, you can imagine that there are many assumes, like for the S factor, they use this phantom of an average man. And also they assume that organ has a uniform activity. However, in the real clinical situation, there is no such a uniform activity distribution along the organs. And also each patient have different organ anatomical relationship. So it is not patient specific. So to actually solve for the solution of this kind of limits of organ-based dosimetry, there has been a Voxel-based dosimetry, and it is based on the assume that these voxels are regarded as single organ, and for each voxel they do Monte Carlo simulation to get the voxel S value. And actually the beauty of this Voxel-based dosimetry is it is independent to standard human anatomy, And it is actually heterogeneous activity distribution is acceptable in this method. However, the problem is that this actually, by doing this for all the boxers, they have to do the Monte Carlo simulation. So it may take too much time and cost. So recently, Professor Jae-sung Lee and Dr. Min-sun Lee have proposed a more simplified method, which will actually reduce the cost and time, and at the same time can give very exact personalized dosimetry. So these will be actually discussed more from the following lectures from Professor Jae-sung Lee and Dr. Min-sun Lee. So now, after learning these kind of dosimetry, what we actually have to, or we should progress is that we should actually design such a clinical trials applying this dosimetry. So actually, it may be better if it may be good for us, because we are a following group for this radiodiagnostics. We are actually right now starting the clinical phase 1 trial for lutetium dotatate, and also phase 1 clinical trial for PSMA, which is already done in other countries. So at the initial, because it is the initial time point, we can actually apply this personalized dosimetry. And if we give more evidence of this efficacy of this personalized dosimetry, actually it could later on be applied to our clinical practice. So I would like to introduce our speakers. So Professor Jae-sung Lee had received his PhD biomedical engineering from Seoul National University, and he joined SANU College of Medicine in 2005, and he is currently a professor of nuclear medicine, biomedical engineering, and biomedical science. So he has achieved academic achievements in various fields, from image analysis to the development of PET systems. So now he is focusing on answering challenging questions in various medical imaging modalities, and including the personalized dosimetry. And Dr. Min-sun Lee has received PhD of radiation applied science from Seoul National University. And she now have joined Korea Atomic Energy Research Institute, where she is currently a senior researcher. She has achieved an academic achievement in medical physics in image acquisition and also Voxel-based dosimetry. So following sessions will be delivered by Professor Jae-sung Lee and Dr. Min-sun Lee, and again by Professor Jae-sung Lee. And after that, we will have some session for question and answers and discussion. And in between all these sessions, I would like to encourage all to give us some questions or comments that we can discuss later on. So thank you very much. And I would like to again welcome all to our 2021 TEIN workshop. So I think we may have, so do you have any questions or comments between?
Yeah, Professor Su. Mati ya? Mati. Yes, Professor Su. Hi, I'm Hendra. How are you?
How are you? Nice to meet you.
Nice to meet you again here. I have one question. It's written that the limited dose for kidney is 23 gray and bone marrow is 2 gray. but it's in one of your lecture, it's 20 gray is the accumulated dose. It is 20 gray is for one cycle or for all the cycles?
Oh, so the strategy is actually different. Like for this study, the sum of the total dose delivered to the kidney is 23. They have prescribed the dose for the first 5 gray, and for the 2, 3, 4 cycle, they have prescribed for each 6 gray. So the sum is 18 gray. So all the sum will be the reaching the dose to the kidney for 23 gray, which is a known some threshold for the kidney toxicity. However, actually, it's these kind of toxicity studies are not well established for this lutetium dotatate or PRT therapy. So the 23 may not be the gold standard threshold. So actually this group have found that they can give more for the threshold. So what they have done was they firstly chosen the dose of some to the kidney of 27 gray. However, the patient who did not have any toxicity and who have response to, they have given more, summing up to 40 gray to the kidney. So it is not for the every cycle, but the total summation to reach like 27 or 40, or in this study, it might be 23.
Okay, thank you. Thank you, Professor.
Thank you.
Hello, can I have a question?
Yes, hello.
Yeah, good afternoon. Thank you
Good
for
afternoon.
the great presentation. So, following the question from Dr. Hendra, do you mean that the limiting dose for every protocol or every treatment will be different?
Right, so administration dose for every cycle is adjusted based on so for this study, actually it was adjusted based on the prior scan. So from the prior scan, they can actually measure the dose to the kidney. So then what they can do is they can adjust the dose, which will reach the kidney dose to 6th grade. So, and the third, they also get the information from the prior scan and they adjust the dose to reach the kidney dose to 6th grade again. So the absorbed dose to the kidney is always same at 2nd, 3rd, and 4th therapy to 6th grade. However, as you can see here, that the actual administered dose is every cycle it is differently administered.
Excuse me, can you make it bigger?
Sorry, yeah. Yeah, so the dose which was actually administered is actually different for every cycle. So they adjust the dose, not giving the fixed dose, which is as in the Lutathera like 200 millicurie, but they not doing that fixed dose. They adjust the dose every time according to the prior scan. And actually for the first therapy, because there is no prior scan, how they calculate the dose was based on the BSA and GFR of the patient.
Okay, understood. Thank you for the answer.
Thank you. Thank you for the question. Yeah. Okay. Do you have any more questions or comments? Or I think we can move on to the next session, but if it's okay for Professor Jason Lee, could we start 7 minutes later from at 50 minutes? Will it be okay for?
Yes, okay.
Okay, then meet again after 6 minutes. And in between, at the break time, I'd appreciate if all the participants can fill out the questionnaires. Actually, we have put a link in the chat. So in between the lectures, if you can fill out the questionnaires, we can act, and if you can give us some comments, we may improve our workshop contents, and we may meet you again with better content. So I would like to appreciate you all to fill out the questions. Thank you, and meet you again at 5 minutes later. Thank you very much. It's time. So Professor Jason Lee will deliver the lecture about basic physics for internal dosimetry. So please welcome Professor Jason Lee.
들리나요?
네, 잘 들립니다.
네. Good afternoon, everyone. As you know, Professor So introduced, my name is Jae-sung Lee, and I'm also in Department of Nuclear Medicine of Seoul National University. Today, that I will provide you 2 lectures. So, one of them is, about basic physics for internal dosimetry. The second one will be the Voxel-based dosimetry that were given after the Dr. Minson's lab, Minson listener, the lecture. Yeah, the first one is, the basic physics. So in this lecture, I will tell you some basic physics related with, the internal dosimetry. Okay. So as you know, there are 2, different, types of ionizing radiation. So yeah, one of them is, the particulate radiation. So that is, the atomic or subatomic, particles that is, accelerated. So such as electrons and, the protons. Yeah, because these particles has, the mass, so actually we can define the kinetic energy of, these particulate, radiations. The other type is electromagnetic radiation. So that is, oscillating the electrical and magnetic field that transfer, through the space at the speed of light. So actually, that the electromagnetic radiation is a wave-like or the packet of energy. So that is why, we call it the photon or, quantum. And it doesn't have, any mass or electrical charge. So you can see here the relationship of, the frequency and wavelengths and energy of, electromagnetic, radiation. So as you may know, the energy of, electromagnetic radiation is related with, the wavelengths like this. I mean that the energy of electromagnetic, radiation in the unit of kilo electron volt equals to 1.24 over the lambda. Lambda is, wavelength in the nanometer. Okay. Actually, that the frequency and wavelength is, inversely proportional to each other. So I mean that if we multiply the frequency and wavelength, it equal to the the speed of light c, like this. Okay. So that is why, that with, the higher frequency, the electromagnetic wave, have, higher energy. Okay. So Yeah, actually, that you can see that relationship here. I mean that as you know, gamma ray and X-ray, has higher energy than UV or infrared or microwave. And actually, that they have the high frequency than the others. Okay. Yeah, actually, that the interaction of the electromagnetic wave and particulate radiation, ionizing radiation, are quite different from each other. So that is why we need to to understand the interaction mechanism of the photons with the atom and particulate radiation with atom. Yeah, actually, that in this slide, I summarized the photon interaction of with atoms, 4 different mechanisms. I mean, the first one is Rayleigh or coherent scattering, and the second one is Compton scattering. Third is photoelectric absorption, and the last one is pair production. The Rayleigh, actually, Rayleigh, I'm not sure whether you are familiar with Rayleigh scattering, because this Rayleigh scattering occurs mainly with very low energy photons. So that is not used in nuclear medicine for in vivo imaging. Yeah. By the way, the actually in this Rayleigh scattering, the scattered photon change its direction like that, but the wavelength of a photon remains same as instance photon. I mean that there is no change in the wavelength, so there is no change in the energy of the photons, the instance photons. So it means that no the energy loss is involved in this interaction. So it is quite difficult to identify whether this scattering has the happened or not. Okay. So another type of scattering is Compton scattering. The Compton scattering is different from the Rayleigh one, because in the Compton scattering, although that the photons change its direction like that, actually the energy is also changed. I mean that some energy is lost here, and the photon change its direction. Okay. And because that the photon lost its energy, the wavelength the increase like that. So you can see here the lambda 2, the wavelength of scattered photon is longer than the wavelength of incidence photon. Okay. Then how was the energy spent in this interaction? Actually, the energy, the lost energy, so was used to the eject, expel the Compton electron like that. Okay. So actually, to the emit this electron, the energy of instance photon should be higher than the bounding energy of this electron, and the remaining energy is used as the kinetic energy of Compton the electrons like that. Okay. This Compton scattering is predominant interaction of photons in the diagnostic energy range with soft tissue. Okay. And this interaction, this Compton scattering, is most likely to occur between photons and the outer shell, electrons, as you can see here. Okay. And the energy of Compton electron is dependent on this angle of diffraction. Okay. Generally, with larger the angle of diffraction, more energy is lost here. So the Compton electrons will have the higher kinetic energy. Okay. Yeah, another the photon detection that we should the study we should remember is photoelectric absorption. Yeah, actually that in the photoelectric absorption, the instance photon disappear after lose all of its energy, and this energy is used to detach the expel the photoelectron like that. Okay, so the energy was also used to is used to the expel the photoelectron like that. So the energy of instance photon minus the binding energy of this electron will be the kinetic energy of this photoelectron. Okay. Yeah, actually that if this photoelectron is emitted from the inner shell of atom, then it will make some vacancy here. So if there is some vacancy of electron in the inner shell, what will happen? Yeah, so if there is vacancy here, the electrons in the upper shell, is likely to move to the inner shell to fill this vacancy. Okay, so the overall energy will be decreased. So this energy should be emitted. So that is why that this energy is emitted in the form of characteristic X-ray. Okay. So the characteristic X-ray usually follow the photoelectric absorption. Let me move to the last one, the pair production. So actually, that the pair production is the reverse interaction of the mutual annihilation. I mean that in the pair production, the energy of instance photon is transformed into the electron and positron pairs. I mean that the energy of instance photon is lost, but the energy is used to create this electron and positron. Okay. Yeah, this interaction only occurs by a high energy instance photon that is larger than 1 mega electron volt. Okay. Yeah, and actually, that the following this pair production, the mutual annihilation usually happen. I mean that once the positron is created by this pair production, it is very likely that the positron will meet surrounding neighboring electrons, and they will lose their mass, and their mass will be converted into the gamma ray again. So in this interaction, one instance photon coming and two gamma rays are generated, and one electrons are also generated. Okay. Depending on the energy of photon, instance photon, the relative importance of three major types of photon interaction is different. I mean, in the relatively low energy of photon, the photoelectric effect is dominant. And with the energy between 500 to 0 about 5 mega electron volt, the Compton effect is dominant, and over the 5 mega electron volt or something like that, the pair production is more dominant. Okay. So before I move to the particulate radiation, so do you have any questions? Yeah, if you have any question, so you can, turn on your microphone and ask me, or you can leave, some message in the chatting window. If you don't have, question now, I think you can leave, the message, while, I will go ahead. Okay. So let me now move to the, the particles, the particles of, ionizing radiation. Actually, that as I told you, accelerated, particles, the behavior as, ionizing radiation. Actually, that they can be, charged particles or uncharged particles. The charged particles include, the alpha particle and proton and positron, electron, and beta particle. And the uncharged particle, the include, neutron. So as I told you, the behavior of a particle with charge and mass, passing through, materials is very different from the behavior of a photon. Okay, let me start with, alpha particle. So yeah, alpha decay is, the decay mode that occur primarily among the heavy electrons, as you know. Actually, that this very heavy, unstable element, emit, alpha particle. That equals to the, helium atom. The typical kinetic energy of, alpha particle is about 4 to 8, mega electron volt. And this alpha particle has, very short range. That is about, 0.03 millimeter in body tissue. Okay. The atomic mass is decreased by 4 following, this alpha decay as well. Yeah, another important property, that so we should, know is, this series of decay. So many of, the alpha particles, after, alpha decay, usually this, cascade, the beta or alpha decay, follows. So for example, that if, uranium-238, undergoes, alpha decay, some cascading, the beta minus emission, and additional, alpha emission to follow, this alpha decay. Okay. So that is why, that the alpha particle, the radioisotope, that emit, alpha particle has, the high, therapeutic, the effect because of this, cascading emission of alpha and beta particles. Okay. Another one that we would want to know is beta minus emission. Yeah, actually, that the beta minus emission happens in radionuclide with an excess number of, neutrons compared to the, number of, protons. Actually, that actually in this emission, in this decay, the neutron is converted into a proton with a simultaneous, ejection of negatively charged beta and the anti-neutron. Okay, so it caused the increase of number of, photons by 1, and the atom is transformed into, different element. Okay. So this decay scheme show, the such, the beta minus decay of, carbon-14. So the carbon-14 is one of, pure the beta minus emitter that only, the emitted, the beta minus when it is converted into the nitrogen, 14. Yeah, actually, we can say, they are, pure beta emitters because, that they just, emit, beta minus in this decay. So this, pure, the beta minus emitters include, the hydrogen 3, carbon 14, and phosphate, 32. Okay. Yeah, but actually, that this, the beta minus, emitters, can be used for, therapeutic purpose. But the, the limitation of, this pure beta minus emitter is that, it is very difficult to know where this, radioisotopes, radionuclide, radio tracers are distributed because, no gamma ray or the X-rays are, generated here. Okay. So as you know, that the, beta minus emission, beta minus emission has, the broad, energy spectrum, because as I told you, the electron, actually, that the beta minus is simultaneously, ejected with a negatively charged, antineutrino. So the antineutrino and electron, they share the energy. So that is why, that the energy of, beta minus is determined by chance. Okay. By the way, the maximum beta minus energy is unique for each radioisotopes, and the average energy of beta minus is about 1/3 of maximum. Okay. This beta particle can transparent only, the relatively small thickness of, solid materials. So that is why, that we use, beta minus for therapy. Actually, that the related, the decay mode emission is beta minus gamma. Actually, that the beta minus gamma, emission happens in case, any excess energy in the nucleus following beta decays emit as, gamma ray, internal conversion electrons, and other associated, radiations. Okay. I mean that, that even after the emitting, beta minus particle, the radioisotope still has some excess energy. So this excess energy should be released. So yeah, in this case, that it is released as, gamma. Okay. So this, radionuclide that undergoes, beta minus gamma decay are suitable for a wide range of, applications in nuclear medicine, as you know. One of, most, typical one is, iodine 131 and lutetium 177 is another. Okay. So you can see the, the decay scheme of, one of, beta minus, the gamma emission. So after emitting this beta ray, some gamma rays are also emitted like that. Okay. Let me skip this one. Okay. Then how these, the charged particles, the interact with, atoms. Actually, that there are two different, mechanisms of interaction. So the one of them is excitation. So excitation is the elevation of electrons to excited state in atoms, molecules, or a crystal. Okay. And the ionization is, the removal of electrons from atoms or molecules. So let me check them, step by step. Yeah, actually, that actually, when the heavy, the charged particle move around the, nucleus, actually, that the fraction of instance radiation's energy is the transfer, and actually that this energy is used to make this atom excited. I mean that the electron inner shell is raised to upper shell by the energy of this particle. Okay, so what will happen if this atom is excited? Actually that if this atom is excited, as you saw before, the electrons in the upper shell tend to move to the lower shell to fill this vacancy. So that is why the electromagnetic radiation is generated like that, and this electromagnetic radiation is the characteristic X-ray. Okay, so actually that the characteristic X-ray with unique energy can be generated following this excitation, but this energy can be also used to generate OJ electron. I mean, if there is some vacancy here due to the heavy charged particle, the electrons in the upper shell can move to the lower shell to fill this vacancy and emit some characteristic X-ray. But this energy can be also used to eject some outer shell electrons like that, instead of emitting the characteristic X-rays. So actually that the ejected electron by this mechanism is called OJ electron. Okay, and the kinetic energy of OJ electron equals to the binding energy of inner shell minus 2 times of the binding energy of the outer shells. So actually that this OJ electron is important in the dosimetry, because usually this kinetic energy is lower than the kinetic energy of beta minus the particles. The OJ electron has the higher linear energy transfer than beta minus itself. So the therapeutic effect of OJ electron is larger than the beta minus emitters. I will tell you about it again in my later slide. Okay. The another the interaction mechanism is ionization, as I told you. Actually that the ionization occurs when transfer energy exceeds the bounding energy of the electron. I mean that the instance ionizing the positive or the negative particle the make the some the electrons here in the outer orbit the expelled, as you can see here. Actually this ionization caused by the Coulombing repulsion between this particle and the electron. Okay, so it causes it produce ion pair, the ejected electron and positively charged atom. Okay, and this electron can be used as secondary electron. So usually we call it delta ray. I mean that this electron also causes the ionization of ionization of these atoms, surrounding atoms. Okay. So let me now move to the some the important terminologies used in it. Actually, one of them is specific ionization. The specific ionization's definition is the number of primary and secondary ion pairs produced per unit length of charged particles path. So it should have the unit of ion pairs per milliliter. So actually, that the regarding this of the energy of ion pair, actually specific ionization only counts the number of this specific ionization, the increase with the electrical charge of the particle. I mean that if the electric charge is doubled, the specific ionization will be also doubled. Okay. And specific ionization decrease with instance particle velocity. So it means that if the particle is too fast, the smaller number of ionization will be produced. Because that if the particle is too fast, the interaction probability will be lower. So that is why that the specific ionization decrease with instance the particle velocity. By the way, the value of specific ionization of alpha particle is as high as 7,000 ion pair per milliliter in air, and the specific ionization of electron is ranges 50 to 100 ion pair per centimeter. So as you can see, the alpha particle has higher the specific ionization. Also, that the alpha particle has higher energy than beta particle. So that is why that the alpha particle has higher therapeutic effect. I think you may know about Bragg peak. So Bragg peak is is something like that. Something like this. I mean, so this is the the graph of ion pair. Depending on according to the distance from the end of range, centimeter in air. Actually, that you can regard here as the entrance of the charged particle. For example, alpha particle. So as I said, that the alpha particle, if that the velocity of the particle is too fast, smaller number of ion pairs will be generated because of the lower the interaction probability. But as charged particle moves, the charged particle loses its energy. So the velocity of particle will be also decreased. So with decrease velocity, more number of the ion pairs will be generated like that. So after peak of this ion pairs, actually that the charged particle will have will yield the peak of ion pairs just before it lose all of its kinetic energy. So after losing all of the kinetic energy, this charged particle stop. So this is why we can see some Bragg peak here. Okay. Charged particle tracks. Actually, that the alpha particle and beta particle has different pathway. I mean that because alpha particle is very strong guy, so these are very strong and heavy. It just move in straight way like that. So that is why that the path and the range of alpha particles equals to each other. Yeah, but as you can see here, the beta particles the moves around like that because it is very light and easily that influenced by the surrounding atoms. So that is why the path is longer than the range of the beta particles. Okay. So let me now move to the linear energy transfer. Actually, that the linear energy transfer is the product of specific ionization. I mean that the ion pair per the unit length, and average energy deposited per ion pairs. So actually, this production means the actual amount of energy deposited per unit path length. Okay. So that is why that the linear energy transfer largely determines the biological consequence of radiation exposure. Okay. So alpha and the proton has high linear energy transfer, and electron and gamma and X has low linear energy transfer. Okay. So I mean that the higher linear energy transfer means higher therapeutic effect. Okay. So this slide compares the linear energy transfer of alpha ray and beta ray and OJ electron. So as I told you, the specific ionization of alpha particle is much higher than beta, and the energy of alpha is also much higher than beta. So that is why the linear energy transfer of alpha is much higher than the beta particles. Okay, and beta particle is moving around like that. So it is relatively difficult to break the both of this strength. But because alpha particle move in straight way like that, so actually that it is more likely that it will break the both strand of the DNA like this. Okay. How about the OJ electron? Yeah, as I told you, the OJ electron has lower kinetic energy than beta particle. So the OJ electron, it means that the OJ electron is slower than beta particle. So usually OJ electron lose most of their energy surrounding each origin. So that is why the OJ electron has high linear energy transfer than electrons. Okay, so I think you can compare the range of the linear energy transfer. Okay, so actually so this time in this lecture I told you there are two radiations, ionizing radiations. I mean that the particulated radiations and the electromagnetic wave. Okay, and you should remember that the interaction mechanism of the photons and particles are different with each other. And I told you some important terminologies used in dosimetry. the specific ionizations, and the linear energy transfer. Okay, so do you have any questions or comment?
Hi, Professor Lee.
Hi.
Hi, I'm Hendra. How are you?
Yeah, I'm very fine.
I would like to ask about characteristics X-ray.
Characteristic X-ray, yeah.
Yes. Can we use it as a diagnostic tool? Can we use it as the tool for imaging?
Oh, yeah. Yeah, so yeah, actually, that if character X-ray is generated, so you can utilize that, the characteristic X-ray for the imaging. So yeah, actually, that many of alpha particles and beta particles, cause that characteristic X-rays. So any kind of X-ray or gamma ray that can be utilized for the the imaging of the such radioisotopes for therapeutic purpose.
Okay, thank you very much.
Thank you. So do you have any other questions? Yeah, if not, let's so let me see you again in the last lecture. Thank you.
Thank you, Professor Lee. I think we can start. We may start 10 minutes later. So we will start at 1:40 for Indonesian time. And Dr. Min Sun Lee will deliver us a lecture. Meet you at 10 minutes later. Thank you.
이재성 교수님, 안녕하세요. 그 화면 꺼주시면 제가 이거 공유할게요.
깜빡 잊어버렸네. 잠깐만. 네.
I think it is time, and Dr. Linson Lee will deliver a lecture of organ-based dosimetry, which is now used as a standard method in nuclear medicine field. So please welcome Dr. Minson Lee.
Thank you very much for introduction, Dr. Sa. Hello, my name is Minsun Lee from Korea Atomic Energy Research Institute, and I will be giving a lecture about organ-based dosimetry today. So during the lecture, if you have any question, please feel free to ask any question. This is the context of this lecture. I will briefly go through the basic background, and then we will go through the calculation of radiation dose. And then finally, I will be showing a simple example of organ-based dosimetry using a commercial software called Olinda EXM. In the first session of basic background, I will be talking about the terms and concept that is widely used in the radiation dosimetry. So I guess you already know a bit about radiation dosimetry throughout this previous lecture today, but for your reminders, I would like to introduce a few terms and concepts of the radiation dosimetry. So in a general terminology, radiation dosimetry is defined as the measurement of the deposited energy in the human body that is delivered by the ionizing radiation. Biologically, it means measurement of the radiation-induced changes in the body organism, and physically, it means the measurement of the deposited energy per unit mass of kilogram. This radiation dosimetry terminology is widely used throughout medical fields such as nuclear medicine, radiation oncologies, and also other environmental radiation assessments as well. However, in this lecture today, we are going to focus on the internal radiation dosimetry, especially that is used in the nuclear medicine. So the definition of internal radiation dosimetry is to measure the radiation energy deposited in the internal organs of human body that is specifically delivered by the radiopharmaceutical uptake in the patient. And from now on, I will be focusing on this internal radiation dosimetry concept, especially for the nuclear medicine only. And also regarding the internal radiation dosimetry, I would like to point out that the radiation dose inside the body cannot be measured directly. So it is very challenging to measure the radiation dose inside the body compared to other radiation dosimetry, such as external radiation dosimetry that you put external beam to the body. That is a bit much easier to measure the radiation dose values. However, it is very challenging to measure the radiation dose inside the body. However, it is also very important because we need to analyze the energy distribution in body tissues quantitatively to ensure that the patient get the accurate therapeutic prescriptions. And also it is very important to assess the potential risk for the patients as well. So the basic terminology that is widely used in the internal radiation dosimetry is the absorbed dose, which is described as alphabet letter D. This absorbed dose is defined as amount of radiation energy that has a unit of joule, the energy deposited in the unit mass kilogram of an organ. So based on its definition, the absorbed dose has unit of joule per kilogram. Based on the SI unit, we widely use the unit of Gray, which is GY. I guess you already have seen this unit a lot. And 1 Gray is equal to 1 joule energy deposited per kilogram observer. So this Gray unit is exactly same as 1 joule per kilogram. Based on the traditional unit, people use rad, the unit of rad, and this 1 rad of absorbed dose equals to 0.01 Gray of absorbed dose, and this is defined as 100 ergs of energy deposited per gram observer. This absorbed dose terminology is not only specified in the internal dosimetry. This terminology can be also applied to any kind of observer material. So just remember this absorbed dose has a unit of Gray that is based on the SI unit. The second terminology that I would like to introduce is equivalent dose, that is shown as alphabetical letter H, and the effective dose that is shown in alphabetical letter E. This two terminology is very similar to the absorbed dose unit, which was the energy deposited in each of unit mass of organ. However, these two parameters takes into account of the relative biological damage that is caused by the radiation interacting within the tissue. So the definition of equivalent dose is defined as tissue damage per Gray, which was the absorbed dose, per Gray of the absorbed dose. So since I mentioned that this equivalent dose and effective dose take into account of the biological effects, first of all, they depend on the type of radiation and also the energy value of the radiation. Also, it depends on how exactly each of radiation deposits its energy in the tissue. So this equivalent dose and effective dose can be simply calculated by just simply multiplying the absorbed dose with the weighting factor. Oh, and before that, this two equivalent dose and effective dose has the unit of sievert, which is shown as SV. So this equivalent dose is simply calculated by multiplying the absorbed dose Gray with the weighting factor WR. And WR is, you can check out the weighting factor of WR in this table on the right top. So this is the weighting factor for different type of radiation. So if you use different type of radiation, such as X-ray, gamma ray, electrons, the weighting factors are all equals to 1. So which means that when you use the radiation of X-ray gamma rays, you will have exactly same equivalent dose to the absorbed dose. However, if you use protons, the weighting factor will be 2, and alpha particles, which deposits more energy to the tissue, you will have like weighting factor of 20. After calculating the equivalent dose like this, you can calculate the effective dose of E by multiplying the equivalent dose with the weighting factor WT. And this WT is tissue weighting factor used for calculating the effective dose that you can check on this table. So depending on your organs or tissues, you will have the different weighting factor. So for example, for red marrows, colon, lungs, and stomach, you will have a weighting factor of 0.12. Compared to this value, in case of brain, skin, and bone surfaces, which are like relatively pretty much not affected by the radiation, they have very small weighting factor of 0.01. So by considering the biological damage, depending on the tissue, you will be able to calculate the effective dose like this. So this was the basic background terminology I explained for the understanding the radiation dosimetry. And from now on, I will be talking about how to calculate the radiation dose. In this chapter, I'm going to focus on the method that is introduced by a MERD committee, and which is called the MERD method. So how can you calculate the radiation dose inside the body? As mentioned earlier, as mentioned in the first slide, the radiation dose inside the body cannot be calculated directly. So internal radiation has to be measured based on the image-based analysis. So generally in nuclear medicine field, we use PET or SPECT images for the image-based analysis, since the PET and SPECT can provide quantitative images. For example, PET voxel contains radioactivity information. Each voxel has the unit of becquerel per milliliter. So one of the example of image-based analysis using PET or SPECT imaging is the standard optic value, which is called SUV. So by drawing an ROI region of interest on the PET image, you will be able to pick up the radioactive information within that ROI region, and you will be able to calculate the SUV. This SUV value is used widely for quantitative analysis using the PET images or SPECT images, but this value is a kind of semi-quantitative method to analyze the radiation source distribution within the object. So therefore, this SUV value does not represent the dose at specific organ. It just shows you some kind of radiation source distribution that is relative to the other region. So how can we extract those information from the images? First of all, we need to have a pharmacokinetic distribution. Since depending on the radiopharmaceutical distribution throughout the time, you will have different dose values inside the organs. And to obtain this distribution, we need to take a dynamic PET scan to have the time series radioactivity distribution. And based on this pharmacokinetic distribution, we need to have a proper dosimetric models to calculate the dose values accurately. So in order to calculate the dose values accurately from the pharmacokinetic distribution, there is a one committee called Medical Internal Radiation Dose, which is called MERD committee. And this committee is within the Society of Nuclear Medicine, SNM, and was established in 1965. The purpose of this committee is to develop standard method and models, mathematical schema, and publish the data for assessing the internal radiation dose. So this committee is specifically focused on the internal radiation dosimetry in nuclear medicine. There are a series of reports that is called MERD pamphlets, as you can see in this right figure. And this MERD pamphlet contains very useful information about dosimetric information, dosimetric information, and also methodologies, and also data, published data as well. So the MERD pamphlet number 21, this is the latest publication of MERD-based dose calculation method, So if you're interested and if you want to have further information, please check out on this MERD pamphlet number 21. So from now on, I'm going to explain how to calculate the organ-based doses based on the MERD schema. So MERD schema, organ-based dosimetry that I'm going to talk about today is basically suggested by the MERD committee that I introduced in the previous slide. And we also call this as MERD schema. So organ-based dosimetry means calculating the radiation dose in the organ level. So by each organ, we are going to calculate the absorbed dose that is delivered by the neighboring source organs. This organ-based dosimetry method is considered as a gold standard method in the nuclear medicine field for the internal radiation dosimetry. So the MERD committee suggested to define the absorbed dose, D, that we went through from the basic terminology session. So, and they define the absorbed D of a target region, RT, that is absorbed by the energy delivered by activity in a source region, RS, and this is calculated as this below equation. So this absorbed dose values are simply calculated by multiplying the A tilde, which is called cumulated activity. And this cumulated activity is defined as total number of disintegration in a target region. And by multiplying the cumulated activity with S value, that is defined from the MERD committee, and we will be able to calculate the absorbed dose in unit of Gray. So continuing from the previous slide, the absorbed dose was able to be calculated by multiplying the cumulated activity with the S value. So I would like to explain more about the S values that is suggested by the MERD committee. And this S value is defined as the absorbed dose to a target region per unit activity in a source organ. And as per the definition, this S value has the unit of Gray per becquerel second. And you can check on the unit of cumulated activity by multiplying these two parameters. You will have the unit of Gray, which is the absorbed dose. And this S value depends on the radiation type and also the radiation energy and also the anatomical relationship of organs. And the S value, if you want to calculate it, it can be calculated like this equation, and each of the parameters are like mass of target organ, and this phi is absorbed fraction, and also the equilibrium absorbed dose constant. And I will be talking about each different parameters in the following section. So continuing about the S value, this S value can be calculated based on this equation that I previously shown in the previous slide. And also it can be simulated by using the Monte Carlo simulation based on the generalized mathematical phantom. Since this mathematical phantom looks like this figure on the right bottom, and this is called a generalized phantom. This is called average man phantom. This has a shape and also organ anatomical distribution that has a generalized looks like generalized man, mass, and distributions. Also, I would like to point out that when we calculate the S value, we are based on the assumption that all the organ inside the body has a uniform activity distribution and also uniform medium distribution. But in fact, it's not like that, right? And also the S value, there is already a large database existing for various radionuclides. So you don't need to calculate S value at every time. You can just look up on the Merck pamphlet number 11 or other publication data to check up on the radionuclide you are interested in. And there are already a lots of data, so you don't need to calculate it every time. So from now on, I will go through each step of MERT-based organ dose calculation procedure. And as I mentioned previously, you need to have a pharmacokinetic distribution to assess accurate radiation dose inside the human body. So here we are going to assume a case of dynamic imaging. First of all, we will need to have a series of PET scans starting from 1 minute until end of 2 times longer than half-life of the radionuclide that you're going to use. So in this case, we have 8 different time series PET scans, as you can see in this figure. And based on the PET scans, now we will start to calculate the organ doses that is in our interest. So I tried to divide the whole procedure into 5 steps. And after we acquire dynamic PET scan, first of all, we need to define the source and the target organs. So inside the human body, after the radiopharmaceutical uptake, all the radiopharmaceutical is distributed in the whole body and organs, as you can see in the PET images. And all organs, since there are uptakes in every organs, so all organs can be either source or the target. So for example, if we want to calculate the observed dose value in the liver, we first need to consider the radioactivity inside the liver itself. So we will have a self-irradiated dose from the liver. And also we need to consider the neighboring organs such as heart, lung, intestine, and kidneys as well, because the radiation uptake from the lung will also affect the liver and deposit its energy on the liver. So firstly, we need to remember that all the organs can be either source or the target. So for this lecture, we will focus on the liver, for example. Once we define the target organ, and also we try to find out the source organ, as a second and the third step, firstly, we need to obtain the time activity curve of the source organ. And then as a next step, we are going to calculate the amount of activity and the time spent in the source. So at this step, based on the equation that I showed you in the previous slide, we are going to calculate this A tilde, which is the accumulated activity. And I would like to say that this step is most troublesome because based on the patient, there are many variations existing, such as metabolism, and also radiation distribution is all different, and this is based on the disease state, it's all different. So you will need to have accurate radiation distribution from the corresponding PET scans. So at this step, I mentioned that we are going to calculate the A tilde, which is the accumulated activity. So I hope you remember that as a first step of MERT-based organ dosimetry, we took a dynamic PET scan. So we have a time series PET scans. So we are going to draw an ROI on the liver because liver is our region of interest, for example. So you're going to draw an ROI on the liver, and we will be able to calculate the radioactivity information inside the liver itself. And based on by drawing ROI at every time series PET scan, we will be able to draw a time activity curve like this. So time activity curve is the activity information at each different time points. And by taking the dynamic PET scan, we will be able to draw this curve for each different organs. And by integrating the area under curve of this time activity curve, we will be able to calculate the accumulated activity. So the unit of accumulated activity is megabecquerel per second, which means that by integrating this area under curve of activity to the time, so this is the this becomes accumulated activity. So this accumulated activity can be defined as amount of total activity present in the source organ during the length of time for which the activity is present. So the best thing is you need to calculate the cumulative activity of each organ until all the radiation is gone. So it will be about like 4 times of the half-life. Another similar terminology that you can use instead of cumulative activity is the residence time, which is also called the average lifetime. This average lifetime this residence time is defined as average lifetime of a radionuclide that is in the source organ. And this is almost same as the accumulated activity. So residence time can be simply calculated by dividing the accumulated activity with the initial activity of the injected dose. So this residence time will have the unit of per second, and this can be defined as total number of disintegration per the unit activity. So we have done step number 2 and 3, which was calculating this E tilde. And then we will move on to the step number 4, which is calculating the total amount of energy emitted by the radioactivity in the source. So I have shown you that this S value can be expressed as this equation. And at the step 4, we will be calculating this delta I. So this delta I it's kind of a parameter that contains information about the physical characteristic of a radionuclide, also including information of energy and also frequency of radiation. So since with the this step is very important because since if you are using the different radionuclide, it has different emission energy and also different frequency of emission, which means that the energy delivered to specific organ will be different. So depending on the radionuclide that you are going to use, you will need to have a different delta I value. So this delta I is called equilibrium absorbed dose constant, and it has a unit of gray kilogram per becquerel second. And this is defined as the energy emitted per unit cumulated activity. And I just mentioned that this constant depends on the radionuclide emission type. So this delta I can be calculated as this equation, and we need to consider the EI, which is the average energy of ith emission of specific radionuclide, and NI is the relative frequency of the emission. And this is a conversion factor of 1 MeV to joule energy unit. And for depending on your radionuclide that you're going to use, you need to consider the absorbed dose constant that is based on the X-ray, gamma ray, beta ray, and alpha ray, and etc. So by considering every emission type, you will have the final delta I value, and this delta I will mean the radiation energy emitted by ith emission in the source organ. So as a final step of organ dose calculation, we will going to calculate this phi factor in this equation. And this means the fraction of energy emitted by the source organ that is absorbed by the target organ. So this fraction, this parameter will depend on the patient anatomy. So for example, when we are calculating dose at the liver, the radiation from the stomach to liver and also radiation from the kidney to liver will be different due to their geometrical position and also due to their shape, depending on the patient. So we need to calculate each of the fraction of each of absorbing energy fraction, depending on the type of organ and different organs. So this phi is called absorbed fraction, and this is defined as fraction of energy emitted by the source organ. So for example, if we say the source organ is kidney and target organ, we see the liver. So fraction of energy emitted by the kidney that will be absorbed by the liver. So this absorbed fraction will depend on the amount of energy reaching the target organ and also the volume and also composition of the liver, target organ, and also the type of energy of the emission, and also the anatomical relationship of the source target pair. For example, here it will be liver, it will be anatomical relationship between liver and the kidney pair. And this absorbed fraction has to be determined for each type of radiation from radionuclide and for each source target pair for the in calculation. So based on the source target pair, it will be defined as phi from source region to target region, like this equation. And this is defined as absorbed fraction for energy delivered from the source region to the target region. So depending on the radionuclide, and also depending on the source target pair, this absorbed fraction will be calculated. So we went through every step of organ dose calculation that is suggested by the MERT committee, and we calculated the cumulated activity at step 2 and 3 by using the dynamics PET scan and by integrating the area under curve of the time activity curve of each target organs that you want to have the absorb dose value. And then we also calculated the delta I, which was the dose constant that has that contains information of radiation, energy, emission type. And finally, we have calculated the absorbed fraction that has dependency on the anatomical relationship, depending on your source organ and target organ. And by summing by multiplying the absorbed fraction and dose constant and summing it for each of radionuclide, and by multiplying with E tilde, which is cumulated activity, you will have the total energy absorbed dose. So yeah, so the final, going back to the first absorbed dose equation definition, we will have the final equation of average absorbed dose like this. So by dividing the total energy absorbed dose with the organ mass, mk, we will have the absorbed dose. And then this can be simply defined as E tilde times S value. So this very complicated equation will be equal to S value. So all the procedure maybe sound like very complicated, but oh, don't worry, since you don't need to go through every step, because as I mentioned, there are already a large database of S values depending on the radionuclide and also depending on the source organ target and source organ pairs. There are large database, as you can see in this table. So you just need to check up on the S values of your interest organ and then multiply with the accumulated activity that you got from the dynamic PET scan. So I went through the organ-based dosimetry procedure that was based on the merge schema. And finally, I just wanted to show you an example of organ-based dosimetry by using a commercial software that is called Olinda EXM. So there are several commercial softwares to calculate the organ doses. And today I'm going to show you an example of Olinda EXM, which is an abbreviated version of organ level internal dose assessment with exponential modeling. And this Olinda EXM is developed by the Radar Group, and they contain over 1,000 radionuclide, including alpha emitter, which means that they have a large database of S values. So here you don't need to calculate the S value every time. And they have different models for different phantoms for adults, children, and pregnant women, which means that they have different observed fraction information depending on the adult model, children model, and pregnant woman model, since depending on adult and children have very much different anatomy, so they calculated the observed fraction for different cases. And they also supports for the Voxel-based realistic phantoms for mouse and rat and dog models. And they also provide the ability to modify the organ masses to the patient-specific values. And finally, they are also able to assign the activity on the walls of the hollow organs, such as bladders, I think. Yeah, so Olinda EXM provides this kind of many different options. And there are also other commercial software that is called MERDOS or BigDose. So from now on, I'm going to show you an example of calculating the organ-based dose values using this commercial Olinda EXM program. When you open this program, you will see this kind of window, and you can see in the top tab. So this is the main input format, and you need to put information of nuclide and also model that you're going to use, and also we need to provide kinetic information that you got from your PET scan. Yeah. And since we haven't provided any information, there is no information related to nuclide and model. So let's start. So in this example, I am going to use the gallium and especially gallium-68. And as you can see, there are many different radionuclide that you can choose, as you can see in this list. And then as a next step, you will be choosing the model input. So in this case, I chose the adult female, but you will have different options of adult male and 15, 10, 5, 1-year-old child, also newborn baby, and you also have an option of pregnant woman. And also there are more specified options of using prostate gland, peritoneal cavity, spheres, head, and kid models. So depending on your choice, you will be able to calculate the absorbed dose with more accurate selection. And then we will going to provide kinetic information. And this part is the most important part of this all in the EXM program. And if you don't provide exact and accurate information of this kinetic input information, you won't be able to have the exact absorbed dose values. So I hope you remember what was the residence time. Just for your reminder, the residence time was very similar parameter to the accumulated activity. On your dynamic PET scan, you will be drawing an ROI on your target organ, and you will going to integrate the time activity curve to have the total number of radiation disintegration inside the source organ. And by simply dividing this cumulative activity with the injected dose, you will have the residence time. So based on the previous slide that I show you again, you will going to provide information about the residence time of each different organs. And also at this step, you can also add voiding bladder model when your patient went to restroom in between the scans. And finally, if we go back to the main window, you will have the you have the nuclide input information and model information. And after clicking this doses value, you will have the final observed dose results. So here we have calculated absorbed dose for gallium-68 that was based on the adult female model. And this is the effective dose, which was the absorbed dose that took into account of biological effects depending on the organs and also the radiation type. You will have the absorbed dose values in the last column. And also depending on your radionuclide, if your radionuclide have like beta and also photon, you will have different absorbed dose that was energy deposited by beta and also photon. You can also differentiate between beta and photon, and this is the total absorbed dose values for the patient. So you can see that this organ-based dosimetry is rather very simple method for calculating the radiation dose inside for the patient. So to summarize the lecture today, we talked about the organ-based dosimetry using the MERT schema. And this is this dose calculation method is suggested by the MERT committee that is from Society of Nuclear Medicine. And they basically calculate the radiation dose in the organ level. So it is called organ-based dosimetry. And this organ-based dosimetry approach is a gold standard in the nuclear medicine field. The advantage of this organ-based dosimetry method is it is very simple, and also you can calculate the radiation dose very fastly. And also it has this organ-based dosimetry is based on the standard model of human anatomy. So we are not using the real patient anatomy information. So we're just using the mathematical phantom that is called general average man. And this can provide the dose assessment for a just general population. So therefore, this organ-based dosimetry is simple, fast, and however, it is not patient-specific. because I just mentioned that this calculation is based on the average mean mathematical phantom, which all the organs are anatomically fixed, and it has a uniform source distribution and also uniform media distribution. So in order to overcome this disadvantages of organ-based dosimetry, people are started to use voxel-based dosimetry technique, which will be presented by Professor Jae-sung Lee in the next lecture. So this is end of my lectures. Thank you very much for your attention, and please let me know if you have any further questions. Thank you very much.
Yeah.
Can I have a question, Prof, please?
Sure.
Thank you, Prof. Which one do you prefer for the dosimetry? Is that gallium PET radio pharmacy or the SPEC radio pharmacy? And for the second question, for the merge schema, is that possible that we can access all the merge pamphlet from the SNMMI? Thank you.
So let me repeat the question. So the first question is comparing the organ-based dosimetry and voxel-based dosimetry, which do I prefer? Is it correct?
That's correct.
So if your purpose of dosimetry is just to assess just radiation doses for general population, I will prefer organ-based dosimetry because it is very simple and fast. But if your purpose of radiation dosimetry has to be patient-specific, I would suggest to use voxel-based dosimetry approach, because voxel-based dosimetry approach considers the real patient anatomy and also the non-uniform radiation activity distribution. So it will provide you more accurate dose values. So depending on your purposes, I think you need to choose between two methods. And for the second question, I'm sorry, can you repeat the second question? It was about merge schema, right?
Yes, about merge schema. Is it available for us to access the merge pamphlets, all the merge pamphlets?
Oh, yes, I think so. If you search on internet, I think you will be able to download the merge pamphlet. And I think the merge pamphlet number 21 is open access, I think. Yes.
Thank you, Prof.
Can I ask your question? Okay, let me ask you some question.
Yes, please.
How accurate Olinda program if compared by other program? You got it?
So comparing, how do I compare the Olinda with other commercial programs?
Yes.
Unfortunately, I don't have any experience using other programs. I just have used Olinda software previously. So I'm sorry, I won't be able to compare between other programs.
Okay.
Yeah.
Okay. I have a second question. So can we set manual for the patient that the example for the age, we don't find the match age that in that program. So can we set it manual?
I think you cannot find the actual age-matched phantom or the model in the Olinda program.
Yes, that's right.
So in that case, how can you dealt with that kind of case which is not actually matching with the Olinda model in the phantom? How can we is it right? How can you personalize that? Or in case there is no model fitting to our actual patients?
So
Yes, exactly.
that's the main drawback of the organ-based dosimetry using a commercial software. So you will have just a option of the software provided models. So you will need to find most appropriate model that corresponds to your patient. So yeah, if you really want to have real accurate radiation dose value, you need to move on to the voxel-based dosimetry technique.
Okay, thank you.
I think just in case of some to actually normalize to apply personalized, in some they do what they do is Olinda gives us how the mass, the weight of each organ for this average man or the phantom they have used. So what we do is we actually normalize patient organ mass according to that average man to actually more fit to the in a personalized order. So that might be some way if you want to apply your patient in this Olinda, you can actually normalize the like cumulative activity in organs based on the organ volume. And yeah, I think that is what people are actually doing for the organ-based dosimetry. And
Hello,
actually, yeah, sorry.
can I ask one more question? Just curious about the residence time that it need to be input in Olinda. How do we get the data of residence time for a specific radiopharmaceutical?
So the resident, going back to the previous slide, number 17, I tried to summarize how to calculate the residence time. So first of all, you will have the dynamic PET scan, right? And when you draw an ROI on your target organ, you will have the time series radioactivity information for each organs. And then you will be able to draw a time activity curve like this figure. So this time activity curve is activity information at different time points. So using your dynamic PET scan and drawing ROI, and you can extract the time activity curve like this. And what we need to do next is we need to integrate the area, and we need to calculate the area under curve of this time activity curve. And this means the total number of district integration in your source or target organ. And then by dividing this cumulated activity with the injected dose, you will be able to calculate the residence time.
Okay, thank you.
Actually, practically, what I want to ask is that formula under in the residence time, actually it can only fit to the mono exponential if the organ has a mono exponential decay. In case whether it is not following such a, is how can we actually get the time the area under curve, like for other practical, in real clinical situations, there might be not fitting to this mono exponential curve. So it might be hard to actually calculate. Is there, what kind of way can we?
Yeah, that's a very good point. So actually, depending on the radiopharmaceutical, the pharmacokinetic distribution will be different. So the best way is to find a good fitting function to calculate the residence time. But for the simplicity, MERD committee suggests to use the exponential function to calculate the area under curve and convert it to the residence time. And yeah, I think
That means if you want to calculate the residence time, we need to do a serial scan for to find the activity to produce a area under the curve. Is that what you mean?
yes, yes.
Okay, thank you. Thank you for the answer.
So actually, it seems that you need more than like 3 of like half-life of this radiopharmaceuticals, 3 times more time of this radiopharmaceutical get. No, at least at least you need to have some scan, like almost to the half-life of this radiopharmaceutical. For instance, like lutetium, you need a, I think, to do a accurate, to get a accurate time activity curve, we might need like more than 5 days after the injection of lutetium. So what I have actually encountered when doing the dosimetry was that in some organs, actually the dose did not go down. Actually, it went like at least for 24 hours. In some case, it went like up. So it may not fit to the mono exponential curve. What I have encountered. So it was that was quite trouble for us to how to deal with that kind of case. And actually, in the Olinda program, it might be an answer that there is a they provide if you put the time and the percent injection percent ID, there is a function. They give a mono exponential or bi-exponential function to calculate the resistance time. So if you use the Olinda program, there is a inside the Olinda program, there is a program that can calculate the residence time. So I think if you have the percent ID and the time, so you may use that also when you want to calculate the residence time.
Thank you for the explanation.
And I think I might have one more question about if we use a planar scan, how can we, what might be the good way to acquire the time activity curve, like, like activity of the organ? How should we define? If we only have like anterior and posterior image in the planar scan.
So the planar image, actually, does it provide you a quantitative image? I'm not sure they are they don't provide the quantitative values in its voxel, right?
Yeah, so actually, like we put a source, known source with known activity, like in between the legs to see the relative uptake. But the actual problem for the planar image is how to calculate the activity. Like using the source, we can get a relative uptake, but yeah, we have some trouble getting the actual activity. So I wondered if you have some experience about how to deal with planar image.
Do you have any opinion, Professor Lee?
Excuse me, Professor Lee.
제가 지금 잘 못 듣고 있었는데 제가 좀 다른 회의에 들어가 있어가지고 질문이 뭐였죠?
플라나 이미지에서는 혹시 액티비티, 이런 타임 액티비티 커브를 다 그리려면 어떻게 해야 될지에 대한 그 액티비티를 어떻게 구해야 하는 게 맞을지, 오르간 액티비티를, 이게 조금 어떤 방법이 가장 적절할지가.
영어로 답하는 거죠? So the question was, how to, the estimate, the activity in the planar images. So, yeah, in the planar image, we use, the standard source. I mean, actually, we usually, the calculate, conversion factor based on the sensitivity of, gamma camera. So that is only based on the point source. So for each organ, usually we can calculate, the total activity. So because it is hard to determine the volume of, each organ. So I think that is only the way that we can utilize for the planar image-based, dosimetry. I'm not sure whether my answer is correct or not.
Actually, what I was curious is that we can actually get a count of the standard source and the organ from the anterior and posterior view.
Yeah.
But actually, the count is not all, and I think we can get the geometric mean, but I think it is not. It does not actually show the depths. It does not actually reflect the depths of the organ. So in that kind of case, how can we get more more exact activity of the organ was actually some
yeah. So actually, that is because because that the estimation of activity obtained based on the planar image is not as accurate as spexity. So I think that is why that the use of spexity is increasing now for dosimetric purposes. So yeah, planar image has limitations.
Thank you for the answer.
Excuse me, Professor Lee. Can I ask a question?
Yes.
I want to ask a question about in this presentation, you said that all the organ can be target or source organ. Is that a mandatory that all the target must be the two of that must be source and target, or can be the organ only be the target but not the source? For the example, I mean, like the brain in the PSMA scan that don't have the then don't get the radiopharmaceutical. Is there a source in the brain? Thank you.
If I can answer, I would say it is not mandatory to check all the organs as a source organ. Actually, you can just choose the source organ as with using just based on the biodistribution of this radionuclide isotope. So if there is no uptake, actually there is no need that you should put it as a source organ. So like as you mentioned about brain or PSMA or like that, it is not necessary, actually not necessary to draw an ROI for every organs that we can answer.
Oh,
Yeah,
okay, thank you.
Yeah, actually, I also agree with Professor. So if that the activity is significantly low, so you don't need to to consider those organs, and particularly for the lutetium 177 and other the beta emitting radioisotope. Actually, the self-absorption of the energy by the organs is very dominant. So relatively to the energy from the other organs. So I think you can focus on some critical organs and the surrounding the organs around that the critical organs.
Okay, thank you for the answer.
Yeah.
I think if there are no more questions, I think we can end Dr. Min-sun Lee's lecture. And if you have any more questions, you can actually give us comments or question at the last session for Q&A and discussion, or you can actually put some comments in the questionnaire. So then we can actually provide you the answer later on after this workshop. So I think I would like to thank Min-sun Lee again for her lecture, and we will have 8-minute break, and let's see 8 minutes later. Thank you very much.
Thank you.
민서 수고 많았어요. 또 봐요.
It is time. So I would like to introduce for our last lecture, Professor Jae-sung Lee, and he will deliver us a lecture of Voxel-based dosimetry, which might be the solution for some limitations of organ-based dosimetry and our standard method. So please welcome Professor Jae-sung Lee.
Thank you, Professor, for your introduction to me again. So as Professor said, the topic of today's last lecture is the Voxel-based dosimetry. As Min-sun told you, the organ-based dosimetry is based on the standard model of human anatomy. And organ-based dosimetry has another limitation because the activity is not distributed uniformly in the source organ in reality. So on the other hand, the voxel-based dosimetry, so that is mainly based on voxel-based Monte Carlo simulation. They provide more accurate the dose distribution. In the voxel-based dosimetry, each organ is regarded as each voxel is regarded as in a single organ or something like that. I mean that each voxel in the image is regarded as source and target of the the energy transfer by the radiation. So this is why that the voxel-based dosimetry is independent to standard human anatomy, and we can also consider the inhomogeneity of activity distribution in our organs. Okay. So as I told you, that the voxel-based dosimetry is more accurate than organ-based one, especially that the voxel-based dosimetry is usually that based on the SPECT CT and PET CT images. So voxel-based dosimetry enables more accurate personalized dosimetry. Because we consider we can consider the heterogeneous activity and the medium distribution. However, the Monte Carlo simulation that is mainly used for the voxel-based dosimetry is very time-consuming operation. So the simple but the faster approach, much faster approach than Monte Carlo simulation has been proposed. Actually, this is simple but the fast approaches include dose point corner method and voxel S-value method. They are quite fast, so they are the more practical than Monte Carlo simulation. But the limitation of this conventional the approaches is that the heterogeneity is usually not considered in these approaches. So that is why we may need the better approach to overcome the limitation of these conventional ones. Okay. Yeah, one of those one of that simple approach is dose point corner method, as I told you. Actually, that the dose point corner means dose point corner is the radial the observed dose distribution around the point source. So actually that the dose point corner is obtained by assuming isotropic point source in the homogeneous the water medium, and usually by performing the Monte Carlo simulation, we calculate dose distribution around this isotropic point source. Then it will yield some dose point corner, as you can see here. I mean that this x-axis is the distance from the point source at the center, and the y-axis is radiation dose. Radiation dose. Okay. So once we obtain that dose point corner, dose corner, actually we convolve this dose point corner with activity distribution. Then it will it will produce some the dose distribution in the heterogeneous activity. Yeah, actually, this method is quite fast because only one dimensional the convolution operation is involved, but it cannot be applicable to the heterogeneous media because we just assume the water medium. Okay. Voxel, the S value is more advanced approach. Actually, I can say the voxel S value approach is a kind of three-dimensional version of this dose point corner. If you look at this the equation, it looks quite similar to the the model schema for organ-based dosimetry using the S values. Actually, it is true because that in the voxel S value approach, we regard each voxel as source and target. So this equation is described what's the amount of those in the target voxel here, voxel J's voxel, from the the surrounding the voxels around these target voxels. So we should consider the activity of each voxel, ice voxel around this target voxel, and the energy transfer from the ice voxel source to the JC voxel target. So we can pre-calculate this the amount of energy transfer. So we can define we can regard it as a voxel S value. Okay. So then by multiplying the activity of each voxel and voxel S value from each voxel to voxel, and by applying the summation, we can calculate the radiation dose in the target voxel. Okay, actually that this the operation is the same as convolution, so we can describe this the approach using the convolution operation, as you can see here. This voxel S value approach is mainly applied to the homogeneous the water medium. As I mean that this voxel S values are the acquired the homogeneous the water medium. So although it is also quite fast, but the heterogeneity of medium is not the constant. So that is why that this voxel S value approach is usually applied in the homogeneous tissue lesions. Yeah, so that is also the limitation of this conventional approach, because as I told you, in the the voxel S value approach, conventional single dose corner based voxel S value approach, we just assume that all of our body tissue is water equivalent. But if we compare the radiation dose map calculated based on the single dose corner based method, there is very big discrepancy in the dose distribution, especially in the lung right here, that has that is quite different from the water, and that some bone regions like that. Okay. So that is why that we can say the Monte Carlo simulation is more accurate approach for voxel-based dosimetry. Several different many different Monte Carlo calculation engines are available, including the the EGS4 and the GM4 and MCMP4. Yeah, but not all of them are supporting those calculation. Those calculation, and usually that we use EGS4, MCMP, and GM4 for the those calculation for medical purposes. So Minsun and I has mostly used gate simulation tool. Gate simulation tool is a script-based simulation tool that is based on GM4 the tool. But it is quite easy to use for the the voxel-based dosimetry. So we just need the activity and the attenuation information and some the setting of the radiation physics. So several papers have shown the the potential and feasibility of gate simulation for dosimetric purposes. So actually, this is one of them. This is the dose distribution overlaid on the mouse CT. So that was obtained from iodine 131 source. Okay. Maybe I think that the iodine 131 labeled radioisotope, the radiopharmaceutical, were injected into the mouse with cancer model or something like that. This figure shows the distribution, calculated using the gate simulation as well. So it was the dose distribution from the iodine 125 in CD for the brachytherapies for the prostate cancer. Okay. Then how we can apply the this gate simulation? I mean that let me explain the procedure of voxel-based dosimetry using the gate simulation step by step. In the gate the simulation tool, we need to prepare the anatomical images and emission images. So the attenuation anatomical image is used for attenuation calculation. So actually that they are defined as voxel-based phantom and voxel-based source in the gate. Then that the gate simulation toolkit will perform some dose calculation in voxel level that is referred as a dosel in gate simulation. So as a result, the simulation tool will yield dose output that is generated as a 3-dimensional image. Okay. So yeah, actually that so this is one of the such example. That if we want actually that we wanted to perform the voxel-based dosimetry of gallium-68 Nuta MGD. So this is the PET image, CT image, and the dynamic PET data to calculate the time activity curve. As I told you, that we should provide anatomical image as a voxelized phantom. So CT image is provides to the simulation, and the image voxel value is converted to each the attenuator based on the ideal the Hans field unit in the simulation tool. Okay. The simulation also need the voxelized source. I mean that the activity, the information. So the emission image like PET in the interfile format should be provided to the simulation tool, and that we need to convert the image pixel value to the real activity. So using the conversion factor. So this scaling factor should be the calculated before performing the simulation. Then once we set the physics environment correctly, the dose actor that is in a simulation engine is the running is run, and 3D dose map and the uncertainty map of dose estimation is calculated. So let me show you the result of the Monte Carlo simulation, the gate-based Monte Carlo simulation. So the left one is the PET image that we used as an input to the simulation toolkit, and the right figure is in a 3-dimensional dose image provided as output of this gate simulation. So we can easily identify the heterogeneous distribution of radiation dose across the organs and inside each organ. We can also apply this voxel-based dosimetry for preclinical data as well. So actually in this study that we wanted to compare the the radiation dose to the critical organ of 3 different radioisotopes. So one of them was actually that we wanted to develop some therapeutic radio tracer for the folate to the rich tumors. So that is why that we attached lutetium 177 to folate and then acquired SPECT CT image of the lens. Then by performing the Monte Carlo simulation, actually we could obtain the energy deposition map according to the time like this. So you can see the unit of the pixel value is joule per second per voxel. Okay. Actually, that this tracer is excreted through the urine, so that is why that the kidney radiation dose is quite high here. Actually, this is second the therapeutic tracer that we have tested. Actually, that we label lutetium 177 to ionize the iron oxide nanoparticle. Actually, that the iron oxide nanoparticle is the excreted mostly that in this case mostly excreted through the the colons like that, the intestines. So that is why that the kidney activity was quite low, and the radiation dose to the kidney, that is critical organ, is also quite low. Okay. And what will happen if we label the iodine 177 to iron oxide and attach folate? So in this case, that the kidney activity was relatively lower than the lutetium folate. So I think that is because of the iron oxide nanoparticle. So through this experiment, this voxel-based dosimetry study, actually that we could confirm that the radiation dose to the the kidney that can be reduced if we use ionized nanoparticle together with folate like that. Yeah, so as you can see, the direct Monte Carlo simulation is very the accurate approach. So but because that we consider the heterogeneous activity and medium distribution. Yeah, but the main limitation of direct Monte Carlo simulation that I should confess is extensive computational cost and time. Actually, it takes a very long time. So it is very difficult to use this approach for the routine applications. So this is why that the Minsan and I have developed the new approaches to fast but accurate voxel-based dosimetry. So I mean that we wanted to develop some voxel-based dosimetry that consider the heterogeneity both in activity and medium distribution, but the computation speed, computation cost should be much lower than Monte Carlo simulation. Yeah, one of such approach that we developed is the multiple voxel value approach for heterogeneous media with non-uniform activity distributions. The another one is deep dose, that is voxel dose estimation method. So based on deep convolutional neural network. Yeah, so
Actually, that as I told you, the conventional, the voxel S value approach. In the conventional voxel S value approach, we have just used in a single voxel S value. I mean that the voxel S value corner only for the water. So we apply these corners to all of the voxels regardless of the tissue types. But there in the multiple voxel the S value approach that we have developed, actually we pre-calculated 3D dose corners for the different tissue types. I mean that these are the 3D-dimensional dose corners for air, lung, water, and bone. Yeah, they look quite different. Actually, that these dose corners has the narrow shape in the hard tissues, but it has very the wide distribution for lung and airs, as you can see here. Yeah. So after that pre-calculated these 3D-dimensional dose corners, we applied each of them to the activity map, as you can see here. So I think you can remember this equation. So this equation is for the voxel S value approach. So I mean that we applied the convolution between the activity image and each of the the voxel S value. Then we can obtain the density specific dose maps like this. Actually, that so this dose map is obtained. So with the assumption that the all of our body is air. So this distribution would be the correct only in the air, only in the air. And because that we assume that all of our body is lung, this distribution would be the correct only for lung. But that would be only correct lung. So that is why that we need to multiply the binary mask for each regions like that. I mean that based on the Hounsfield unit of X-ray CT, we can the segment each of the regions like that. So by multiplying this binary mask with density specific dose map, we can calculate mask dose maps. So I mean that we erased radiation dose outside each of these regions. I mean that we erased incorrect those values right there. Then if we add all of this mask dose maps, actually we can calculate final 3D-dimensional dose maps. So do you think this approach makes sense? We calculate 3D-dimensional those corners for each tissue type, and then obtain the density specific dose map, then multiply the masked image to obtain the masked dose map, and then add all of this data to obtain the final 3D-dimensional dose map. Yeah, actually, the reviewers in the Journal of Nuclear Medicine thought that this, quite makes sense. So I think that is why it was published. Yeah. So, but that the accuracy of 3D-dimensional dose map based on this approach would be depending on the number of medium that we assumed. Yeah, if we just use a single medium like water, it would not be accurate, as you could see before. How about the four regions: air, lung, and water, and bone?
I'm not sure because our body is more complex than only this first segment. So that is why that we also tested this approach with larger number of mediums. So by defining more medium, more regions between the air and lung and water and water and bone, okay, based on their density. This slide show such such accuracy of this approach depending on the number of tissue types that we assumed. So the most left one is direct Monte Carlo simulation. The ground truth, those map generated using the direct Monte Carlo simulation, and based on the single Voxel S value. So as I showed, there is large errors here. But if we use multiple Voxel S values, those maps looks quite similar to the direct Monte Carlo simulation. And error also much smaller than single Voxel S value. And but if the number of the tissue types is greater than 8 or 10, the error would be similar. But the larger is better. Okay. Yeah. So using this multiple Voxel S value approach, I think you can appreciate that we could generate a very Monte Carlo simulation method like those distribution. Okay. But the computation time is much shorter than Monte Carlo simulation because that we just need several conversion operation and masking of the images. Recently, we have also applied this approach to the Lutetium 177 for the Diagnostics data date. So these are the multiple Voxel S value for Lutetium 177. And these are the SPECT-CT image used for this study, and 200 millicurie the data date, Lutetium data date was injected, and SPECT-CT images were acquired several times. And we performed same study, same approach procedures, then could calculate the dose maps like that. So this is outcome of direct Monte Carlo simulation, and these are based on the multiple Voxel S values. Yeah, error is quite low except for some lung and the skins like that. Okay. Yeah, so I can say that the multiple Voxel S value approach is this is relatively simple method, just based on the convolution and the masking of the images. So the computation time is much the shorter than Monte Carlo simulation, as I told you. For example, that the full Monte Carlo simulation required about 4,700 hours, and even we use only 5% of the radiation decay. It takes about 10 days. That is very impractical. But the Voxel S value approach, the computation time is only around 1 hour if we use 6 or 8 multiple S values. So there was dramatic the reduction of computation time. But do you think you can use this approach for your the routine practice? But I'm not sure because that the 1 hour is still the significantly long for routine practice. So that is why that we wanted to develop the another approach that would be much faster than any other method. So this method that we call it deep dose. That is a voxel dose estimation method based on the convolutional neural network deep learning method. So actually that in this approach the X-ray CT and activity imaging is given to the neural network as input. Then the neural network is trained to produce the radiation dosimetry. So I mean that to train this neural network, we provided a pair of the SPECT CT or the PET-CT imaging and the dosimetry calculated using the Monte Carlo simulation. So then this network can infer the relationship between the PET-CT or SPECT-CT data and the Monte Carlo simulation based in the dosimetry. So network was trained using a large number of the patches obtained from dynamic data, and that we try to reduce the error between the Monte Carlo simulation based dosimetry and CNN produced dose distribution. Actually that the training time for these the gallium RGD data took about 100 hours. But once network is trained, the computation, the inference itself is very, very fast. So actually this slide shows the result. Actually that between these two images, the one of them was the computed generated based on the Monte Carlo simulation, and the other one was the generated by applying the pre-trained the neural networks. So can you distinguish them? Can you tell me which is which? Yeah, it is quite difficult. They look quite similar, almost equivalent. But the left one is the outcome of Monte Carlo simulation. That took 200 days if we wanted full Monte Carlo simulation, and took 10 days only for 5% of the radiation decay. Still, it is very, very long time. Yeah, but the deep dose, the convolutional neural network deep learning based method took only about 3 minutes. That is significantly much shorter than Monte Carlo simulation, and even it is much shorter than 1 hour that required for multiple voxel value. So I think that if this dose calculation, the patient based individual based dose calculation takes only 3 minutes or something like that, I would say it would be feasible for the routine practice, practical applications. This method also showed quite low errors, as you can see here. Actually the absolute difference was quite low, except for some urinary activities. I think we can ignore it. Okay. So this slide shows dose rate profile of Monte Carlo simulation and convolutional neural net based approach. Okay. So my conclusion is that this deep learning based the dose calculation approach is very, very fast and as accurate as Monte Carlo simulation. So I think this would be quite the promising approach for to be applied in the routine clinic as an alternative tool to the Monte Carlo simulation. Okay, so let me sum up my presentation for the second lecture. So as I told you, and Minson told you, the organ-based the simulation has the organ-based dosimetry has limitations because we do not count for the variation of human anatomy and the heterogeneous distribution of radioactivity in the organs. But the voxel-based dosimetry overcome all of such limitations of the organ-based dosimetry. But the main reason why that the people has not used voxel-based dosimetry for their practice is that it takes very, very long time for Monte Carlo simulation. However, the multiple new approaches like multiple voxel S value or this deep learning based approach, they showed the each potential to be used for routine practice because of the very rapid calculation time. Okay, thank you for your attention, and let me welcome your questions. Any questions? If you have questions, you can ask me or you can leave the message. Or we can move to the discussion session. Then you can think more any questions and you can ask me or Professor Sir.
Okay. May I ask you, Dr. Lee?
Yeah.
Yeah, thank you for a wonderful talk. And I just want to know, based your experience using this method, Voxel, is maybe is any difficulties, or maybe you ever met when you using this, maybe where, yeah, I just want to know, maybe you can sharing to us. Is there any difficulties sometime you met when you using this method? Thank you.
Yeah, so yeah, as I told you, that the gate simulation, is relatively easy to use rather than other simulation toolkit. So actually it was not so much difficult to introduce this method, to learn this method. But actually that the simulation usually that requires some physics the knowledge. So to get the some feasible result it took some time. So Minson and actually the several, my PhD student has spent several years to set up this method. So there was some difficulty. I mean that the physics knowledge required the physics knowledge for simulation. But there yeah. So and that the further the new approaches
yeah, actually, that it is still under development and still the investigation. So to apply this method, we manually collected the image data and learn these approaches. So that would be the main difficulty. And the difficulty that I should say is that for the this Monte Carlo simulation, I mean that the dosimetry studies, we should frequently calculate sensitivity of the scanners by performing cross calibration. Yeah, but yeah, it takes also time. But I think that is not a significant bottleneck.
Okay, thank you, Dr. Ri.
Yeah, thank you for asking the question. Any other questions do you have?
Hi, Professor Lee.
Wow, howling.
Hi, this is Hendra. If do you have both PET radiopharmaceutical and gamma photon emitting radionuclide, which one do you prefer for dosimetry? I mean, for example, you have lutetium PSMA and also you have gallium PSMA. Which one do you prefer for dosimetry?
Yeah, so it is a difficult question. Yeah, actually, that there between the gallium and lutetium, 177. So for more, accurate, the dosimetry, the dose calculation, the gallium, would have a benefit because the PET has better resolution. Yeah, but actually, that the performing dosimetry based on the gallium is quite challenging because gallium has very short half-life. So, but even we just use the several time point, only several time point. Actually, we need some image data maybe 25 hours after the injection or something like that. But the gallium has too short half-life. So with the gallium, it is quite challenging to obtain the accurate dose distribution. So, but the the lutetium, because gamma ray, the amount of gamma ray emitted from the lutetium is quite low. So I think it would be also very challenging to obtain the diagnostic level, the images with diagnostic level, the amount of the lutetium-based tracers. So if we do the dosimetry using the lutetium based data, actually it will be the dosimetry for the post injection of therapeutic amount of lutetium 177. So it means that it is hard to use it for predicting the radiation the dose. So actually it is quite a kind of dilemma. So maybe I think that we should be we may need very, very smart way to utilize gallium labeled the PSMA for the lutetium PSMA dosimetry or something like that. But I don't know yet what is the possible way. Dr. So, Professor So, do you have any good suggestion?
죄송합니다. 정확하게 질문을 잘 못.
알륨 68 PSMA를 가지고 루테슘 PSMA 도시메트리 할 수 있는 방법에 대해서 혹시 좋은 아이디어 있나요?
Okay. Actually, that may be also our concern, whether. So there are some articles that are showing that as assumable that gallium-68 can uptake from the gallium-68 has a relationship with the lutetium-based dosimetry, but actually it might be, firstly, accurate dose might be hard, but what we can use for the gallium-68 might be we can stratify, or we can at least predict the dose, but yeah, but still, I think there is quite, but the most important problem is that the biodistribution is actually different. Although we use the same dotate, like dotate, it might be different. And actually, like we in our institute, we are using gallium-68 dotatate, but for the therapy, we are using lutetium dotatate. And actually, it has a similar distribution, but it has quite like different uptake in the spleen or so. We are also concerning whether whether it could be used, but right now I don't have that good idea of. Recently, yeah, there has been an abstract from Asan Medical Hospital about that. But it also just showed that there is a relationship, which is actually assumable. Not like there is not to calculate the dose, just the correlation was actually revealed. So yeah.
Yeah, maybe better than nothing.
Yeah.
Yeah. Thank you very much.
So for some, I think there are some times left. So I think we could have some discussion of like practical issues. So I think it will be great if you can share us about the situation or what kind of like procedures are doing for specifically like therapy, and whether like dosimetries are routinely done, or is like dosimetry research is ongoing. If you can share us some experience, and it will be great. So, unfortunately, I don't know that much nuclear medicine physician in Indonesia, but I would like to ask if like Dr. Alexander could share us some experience of the situation in Indonesia. Or maybe if it's hard, if someone could.
Actually, for the dosimetry. Yeah, actually for the diagnostic dosimetry, we have tried some cases with lutetium dotatate and lutetium PSMA. Maybe Ibu Inu can share her experience. Ibu Inu. Ibu Nur Hidayati. Nggak ada ya? Ada. Maybe before Ibu Miss Nur Hidayati answer, may I have question for you, Professor Minsukso?
Oh, yes.
Okay, thank you, Professor. In European guidelines, if I'm not mistaken, they say that the contraindication for lutetium PSMA is low GFR in low GFR patients with GFR less than 30 or 40. But if the patient had undergone some hemodialysis procedures, can we still do the PSMA therapy?
Actually, I am sorry that I cannot actually answer exact to that problem, since actually we don't have any experience lutetium PSMA therapy right now in it's a new age right now. So I cannot really explain, but according, when we think about iodine therapies, like if we can apply hemodialysis, I think it also can be applied to these PSMA or PRT therapy patients, I think. But still, I don't have that much experience to actually, answer to that question. Sorry.
Yeah, I have searched for some journals in the web, but no, I didn't find any journal about it. But what I wonder is why the European guidelines say that is a contraindication, not say maybe just relative contraindications. So because we think if the patient had performed hemodialysis, maybe we can ignore the uptake in the kidney. Just maybe the marrow uptake is just the main concern. What do you think about it?
I have somewhat different thinking, because actually there is some researches that are showing that after the PRRT, the patient who have more change or more decrease in the renal functions are patients who have a decreased renal function in the baseline. So I think, I don't know why they have set that as a contraindication, but I do think that in that kind of patient, although we can do like hemodialysis, but actually it can more affect the kidney function. So it can actually, so I think that's some reason why I think that they have chosen as a contraindication. So yeah, so that I think, so although we can clear, still if we inject, it readily gets accumulated in the kidney parenchyma actually. So there can be still a tubular damage. And so like these PSMA agents are not using the kidney just as a passage, but it actually has a uptake in the kidney parenchyma. So it can have a this like radiation to the remaining kidney. So it can actually make it more deteriorate to these kidneys. So I think that's why they have set it as a contraindication. That's just my opinion.
Thank you very much, Professor. About the dosimetry, maybe I can answer a bit with waiting for Mrs. Hidayati. So we have performed dosimetry for lutetium PSMA and lutetium dotatate. But we use a small dose of lutetium, about 5 MCI, but we don't use any sophisticated software. So we just use it in a conventional way, I think. Maybe that's just my answer.
Can I add something?
Yeah, please. Going on. Yeah.
Yeah, sorry. Yes, actually, because I understand that Voxel-based dosimetry is the answer for, is the best the best method for performing dosimetry right now. But at the moment, like Dr. Hendra said, that we don't have any sophisticated method. However, we try to start from the basic, from the beginning, which we using the MERT16 method for doing the image quantification from serial scans of planar images. And at the moment also, we facing the challenge from the, even we have spec city, but we face challenge some I don't know what you say, the ethical committee, that we cannot perform from spec city three times for the patient. Probably Dr. Henda remember at the moment. So we really start from the basic, which is using the serial scan for patient using the geometrical mean. Then we quantify based the activity based the ROI the organ, and we put all the results into Olinda XM version 1, and we generate the residence time for each patient. I don't know if this is the correct method, but we really want to start from the beginning, just to show that the kidney dose for the patient is safe, and finding the biokinetic for the organ and liver. If my answer is not incomplete, probably Dr. Hendra can add something to. Thank you for the opportunities.
Thank you for sharing your experience. So I think actually we also are imprinting a similar problem right now. We are also doing this dosimetry for in the clinical phase 1 trial of lutetium dotatate right now, and we are also doing based on the planner. And just we although we get some spec CTs, we do also are performing the dosimetry based on the planar scan and also using the Olinda program. But I think there are some like limitations, like according to some like patients with disseminated bone metastasis, how to calculate the bone marrow toxicity actually dose is actually some concern. When now we are planning to move on to the clinical study for PSMA, but actually there might be quite a lot of patients who have that bone, like that kind of many metastases. So I think that Professor, what Professor Jae-sung Lee has provided us about this Voxel-based dosimetry can be a solution, but still, like as Dr. Gayati told us that still, I think taking every time of SPECT-CT might be not feasible for every clinical situation. So I think we should still concern and we should figure out together what might be the best way to do this kind of dosimetry in the real clinical situation. So I think if would there be some more other questions or comments?
Can I the comment on that?
Yeah.
Yeah. So yeah, one of the potential the solution is the hybrid the approach. I mean that the combining single SPECT-CT and multiple the planar images, so sequential planar images. So based on the relationship between the SPECT-CT and the planar image of the one of them, actually that we can estimate the more accurate activity from the the planar data. So yeah, but we know about the approach, but we have not applied it yet, but we are on the investigation. So yeah, I think so maybe someday we can share our experience with the hybrid method with you, but I think you can also try. So but I think that the starting with the organ-based dosimetry based on the planar image would be fine, maybe more than fine. And I think to make the voxel-based dosimetry a kind of routine tools, some user-friendly the software is required, because that the voxel-based dosimetry requires some image registration and drawing the volume of interest on the organs to finally obtain the dose values for each organs. So there are many things to to develop and improve for voxel-based dosimetry for routine use. So many of the groups and the commercial companies are working on that. So some of them are available now, and that there are many more will be available soon, I think so.
Thank you for the comments. Would there be any other questions or comments?
Thank you. Thank you, Doctor. Hello.
Yeah, that's all.
Thank you. I have a question for Professor Lee. Okay, I have a question. I would like to know what the graphic in the presentation about the basic physics for internal dosimetry. I just want to know about the graphic. Is it apply in all type of radiation, like alpha, beta, and gamma, or just in alpha and beta because they have a short length of penetration? Thank you.
Actually, that they can be applied to the only the particle radiation. So yeah, the photons lose their energy in exponential way, just like this. Yeah, but the Bragg peak appears only with the particulate radiation.
Thank you, Professor Lee.
Welcome.
So I think we had quite a lot of time for discussion, and I think now we can end our session, workshop for today. I really like to thank everyone for the participation, and I would like to invite Professor Jae-sung Lee if he could deliver us some closing remarks for this workshop.
Actually, I am not ready to give a closing remark, but so I'd like to appreciate all of your attendance and that the participation and many questions. So I wish it was the useful for your better understanding the current status of the organ-based and the voxel-based the approaches. So yeah, hopefully that these techniques will be helpful for our patient. Okay, thank you.
Thank you. And for some more information, I think the lecture, we have recorded the lecture and our lecture materials, and this video will be uploaded within 1 week. So you can find some information in our website, the NM Portal site. Okay. And I would like to lastly inform you, if you can fill out our questionnaires, it will be very helpful for us to actually improve our contents later on for our workshop. I really appreciate everyone. Thank you very much, and see you again.